Okay, so this is the Perceptron game. I developed this game as a need to sort of teach people the abstract concepts of what happens inside a perceptron. A lot of times people, they approach deep learning and they're really confounded by the abstract concepts of even just sort of the really underlying details of what a perceptron does, how things are connected, how the internals work, and how that sort of makes a difference to the overall or overreaching whole system, or the whole neural network, so to speak. So today we're going to look at and play a first variation that just teaches you the Perceptron game with myself and Mariangel.
Hi, my name is Mariangel. I'm in fourth year computer information systems at Mount Royal, and I'm interested in deep learning just because of how many different applications you can do with it. It just seems really interesting that you can apply this into so many different fields like nursing or for training people on different jobs or anything like that. Just seems really cool to me. So that's how I got into it.
Really what this models is a single perceptron, or a single sort of learning unit within a neural network. What I've sort of positioned at the side here is sort of three images, you could say. Each of these images is 1 pixel by 2, okay? And on the labels of the images, we have what we expect their value to be. So the all black image here as we feed it through our system, we expect the output to be a 0. So you can think of it as sort of an input and then an expected output. It's sort of the way all sort of machine learning systems work, okay? So we have these three images, each represent a different sort of a labeled output. And this form of learning is called supervised learning. And so if I clicked on, say, the middle image here,
Ooh.
Right, and what happens there is it feeds into the perceptron with its input. So you'll see the value of 1 is getting fed into the top input, and then the bottom input is 0. This very top input of 1 represents the bias. And the bias is sort of an offset. You could think of it as sort of in a linear equation solution thing. It's sort of the offset to sort of any problem. It's sort of a static offset or just a fixed offset the network can use to sort of move about a solution, essentially. What we want to do is inside the network or inside the perceptron itself are these three units that represent the weights. And the top one represents the weight for the bias, and it's currently set at 0. The second one, again, is 0, but it's for that input of 1. And then the third one is 0, but it also represents 0. Those values, so the input values are multiplied by the weight value, and then that's pushed through this summation function, which is currently showing 0 at the end here. And it's currently showing 0 because we don't have any weight values, right? We're not doing any multiplication here. So these values are multiplied by the weight units, and then in this sort of box, everything is summed up. What gets passed through here is the activation function, and the activation function, in this case, we're not really going to worry about it. We're just going to assume the activation function just passes everything out the same way. The activation function, though, can be used for a number of different things, and we'll get into that later. The goal here is to balance or find the weights, the single set of weights that will solve the solution for all these values. So what I'll get you to do is just click on one of the weights. Okay, so what you see is, as you click on the weights, they'll rotate values, and the values are 0.25, 0.5, 0.75, 1, and 2. These represent just some arbitrary values. In a real deep learning system, they wouldn't be fixed or just discrete weights like this. They'd be, they'd be values that could be, continuous weights essentially. I just use these weights as sort of a simple system sort of to teach the things. And these weights are based on my physical game that I used to use for teaching, but pre-COVID. So the 1 times the 0.5 gives us a 0.5. And since there's no other multiplication or additions here from the other weights, we only get a 0.5 that pushes through. And you can see that the 0.5 is pushing through. It's giving us an output of 0.5. And the expected value is 0.5, meaning our loss is 0. So when we have a loss of 0, a loss or error of 0, meaning that the answer is correct. It's 100% correct. If we have a higher loss or a loss that's 1 or 2 or 3, that means it's an incorrect answer. Okay?
Okay.
Our goal here is to minimize the loss, or your goal in this experiment is going to be to minimize the loss. So I'm just going to turn you loose here in about 2 minutes, or just 30 seconds or less, and just to look at and balance those weights and to reduce that loss to 0 for all 3 of those images. Okay, so go ahead.
Okay. That's be for all of them, right?
Yeah, it's a single set of weights we want to find for all of them. And that's the way all deep learning systems work, is we want to find that single set of weights that will generalize a problem.
Actually, it doesn't even matter what the other ones are. It's just the middle one that matters, right? Or the middle and the top.
No.
Isn't it?
No.
These are... Is that right?
0.25, 0.25, 0.25. So what happens if you change the image now? So if you click on the top image, the label for the top one. Yeah. Okay, so what's your output? What's your loss?
0.5, 0.25.
And click on the bottom image. What's your loss?
0.25.
Yeah, same.
An expected 1.
Yeah.
So the 3 images are not getting into the perceptron, only these 2?
Well, no, so when we train or look at anything on a network, we feed a single image at a time to train that, or actually we could do it in batches. We feed the images through to train the network, and then our goal is to always reduce the loss, right? So I'm not going to give you there is an equation that I could give you to simplify this task for you, but you still have to do the mathematics. What I want you to do is, in your head, sort of balance those weights to match what the output is. So our loss for each of the 3 pictures should be 0. So we want to minimize the loss to 0 for all 3 of those images.
I see. No, it's 150.
Do you remember what the solution is?
I don't. I think I got it though. Did I? Maybe? No, I didn't.
Well, let's just work through until you find it. We can cut this and edit this part.
So all these weights have to be the same. Right?
Yeah, you're going to set the weights to one set of values, and then you should be able to switch between the images, and there should be, that loss value should be 0.
That's a loss. But no matter what, this one's going to have a loss.
Yeah, and do try and speak out some of what you're thinking as well, because that'll be really helpful.
And then the middle one expects 0.5. But then if these 3 need to be the same.
No. So the confusion is so the weights don't need to be the same.
Oh,
okay. You need a single set of weights the weights are going to be the same for all 3 different images. So you're not going to change the weights for each different image. You're going to keep the weights, you're going to keep that set of weights for all 3 different images. So that's what I mean by the same weights. Not the same values, no.
Oh, okay, I see. Is this right then?
Yes, you did it. So
Yay!
here, mix it up again and do the eureka moment again.
0.5, 1. Let's make that one 0. That one's fine. That one has a loss of 0.5. So make that 0.5. Loss 0, loss 0, loss 0. That's it. Boom.
Yep.
Got
Good.
it.
Great. Awesome.
Yay.
Great job, Mariangel. Good.
Thank you.
Good. Thanks for helping working with us and showing this problem. Thank you very much.
No problem. Thank you.